try to prove the Schur decomposition, right? And the technique we're going to follow, and the big idea, and this idea is actually not just restricted to this proof, but is very important in all of mathematics, is the notion of working with polynomials of matrices. Okay, but when we work with this, we have to do a lot of calculations. I just want to say two things about these calculations first, just so that we know when we see them, we recognize them. The first is, suppose I give you an orthogonal matrix, let's say Q, QH. Let's say Q is a unitary matrix which is satisfying expression. Then we see from the trivial expression, identity times x is equal to x, right? We've seen this many times before, is equal to x, right? So let's call the columns of Q as Q1 up to Qn, right? So then we know that we can write this in outer product form as Q1, Q1h plus Q2, Q2h, like that. So we've done this calculation once before, but I wanted to repeat it before I say something a little bit more general. Is equal to x, right? So therefore we can bring the x in and write this as Q1, Q1hx plus Q2, Q2hx, like that, all the way up to Qn, Q1hx. Okay. So the way we read this expression, of course, it's a tautology, of course, right? But just saying x equal to x. But the way we read it is that if you look at these numbers, then these are just scalars. These are the columns Q1 through Qn. So we see that this gives us the expansion of x in the basis of the columns Q1 through Qn, right? So this is the expansion of x in the basis Q1 through Qn. And the coefficient of the bases are given by Q1. So the coefficient for Q1 is Q1hx, the coefficient for Q2 is Q2hx, like that. Okay, so this is the expansion. So this is also called a change of variable, right? So we're changing, this is called a change of basis. So the original x, of course, is expanded in terms of the canonical basis, that of the identity matrix. Right, so we can write that as E1 transpose x plus 2 E2 transpose x, like that. And now we're changing the basis from the E1 basis to the Q1 basis. And it's easy to do because you just replace these by the Q's instead. Okay? So this is called change of basis. But of course, we don't have to call it anything. We're just saying, I originally have x, I'm writing it like this, and I'm calling this a change of basis. I'm not writing x as a linear combination of the columns of Q. Right? So make sure, if you write it like this, it looks more complicated. If you write it in matrix form, it looks like a trivial. You wouldn't even bother to name the intermediate expression. All right? So, because in Kalmay's book, he prefers writing it that way for a certain reason. So, we're just calling this. Okay, I won't always call this out, but this will happen incessantly. Okay. So, this was with unitary matrices. What happens if I use a non-unitary matrix? Say, for example, I have a matrix V, which satisfies this expression V inverse V is equal to identity is equal to V times V inverse. Okay, so let's say we label the columns of V as V1 through Vn, and let's label the rows of V inverse as W1H, W2H. If you don't like complex numbers, just pretend H is T, okay? So those are the columns, the rows of V inverse. Then you see that if I look at this expression equals identity, you see that it satisfies something like an orthogonality relationship, right? For example, if I look at W1H V1, it is actually a 1. If I look at W1H V2, it is a 0. W1H V3 is a 0, and so on. Right? So in particular, the first row of the inverse of V is perpendicular to all the columns except the first one. Okay, so this is another way to compute the inverse. You just orthogonalize. You find a column that's perpendicular to the rest of it. In fact, you can just pick V1 and make it orthogonal to the rest. You'll get the first row of V inverse. Okay, you can consider it by Gram-Schmidt this way. If you look at W2, the second row of V inverse, it satisfies the equation W2H V1 equal to 0, W2H V2 is equal to 1, W2H V3 is equal to 0, and like that. Right, so the second row of V inverse is perpendicular to all the columns of V except the second column. Okay, so what about these numbers? This 1 that you're seeing, Does it mean that W2 and V2 are perpendicular or W1 and V1 are parallel? They're not. Okay, it just means it's not perpendicular, that one has no significance. Okay, it just means not perpendicular, we can't say it's parallel, okay, for sure it is not parallel. Right, because if it was parallel, then V inverse would be VH, transpose of V. That's generally not the case for V inverse. Right, so because this looks like an orthogonality relationship, these kind of things are useful in mathematics. So these W's, Wi's, are called a dual basis sometimes. Okay, we will not use that word, but when you see it in an abstract setting, this is how they will proceed sometimes. But the way, of course, from a linear algebra point of view, is just this trivial relationship that we're exploiting, right? So now because of that, I can write X also like this. I can write as V inverse X is equal to X. If I expand this in the outer product using the columns of V and the rows of V inverse, I will get V1 W1HX plus V2 W2HX like that, plus Vn Wnhx is equal to X. And this is also a change of basis. So now we're changing from the identity basis to the basis provided by the columns of the matrix V, except these columns are not orthogonal to each other. But since it's invertible, they're linearly independent, right? In the case of orthogonal matrices, we call these as orthogonal projectors, right? These are called orthogonal projectors, right? Remember the picture for the orthogonal case was like this. So we have Q1. So this is Q1, this is Q2, the two unitary vectors. This is the column vector X. If I want to expand X in this basis, I just have to drop parallels like this. And this vector will be Q1, Q1HX. And this vector will be Q2, Q2HX, right? So those are called orthogonal projectors because the action of these two matrices is to drop perpendiculars. Right? Now, of course, there's a similar expansion, similar geometrical relationship for these. This expression over here. So you can see it's still, it changes basis from the E1, E2 basis to the V1, V2 basis. But to compute the projections, we have to use these dual bases, W1, W2, Wn, which are just the rows of the inverse of the V matrix. Right? But the name is dual base. Of course, it's just a tautology. It's just some trivial stuff. Okay. So how do we visualize this? So if I have a column V1 over here and I have a column V2 over there, right? Now they're not orthogonal to each other. And if I have an X that is over here, then we know to construct a linear combination, I must drop a line parallel to V2 and drop a line parallel to V1. I'll get these two columns. This one will be V2 W2H of X. And this one will be V1 W1H of X. Right? So these two operators, V2 W2 of H and V1 W1 of H, are called the oblique projectors, right? Because they don't have a 90-degree angle. So they project X, for example, this operator, V1 W1H, projects X obliquely to V1, and the obliqueness is determined by the other columns, V2. Right? Notice that this is a projector, because if I try to apply the projector to V1, it will go to 0. It's truly a projector, okay, but it's an oblique projector. So oblique projectors are idempotent, but unlike orthogonal projectors, they're not symmetric, right? And when we're doing Gaussian elimination, we were constructing oblique projectors, right? And the obliqueness is determined by the dual basis. So if I want to project onto the first column V1, I want to find a column W1 that is perpendicular to V2. So this guy must be perpendicular, right? So W1 is this column, which is perpendicular to V2. Only when you know that can you write down this W1 over here, because we want to make sure that if you apply projector to V2, this is 0. Right? It sounds weird that you form this awkward column over there, but that's what we did. Right? So this way, when you're doing it algebraically, you barely notice, you don't even pause to give it a name. But in the abstract setting, it's useful to actually call out a name for these expressions. So these are the oblique projectors. Right, and the rows you need to write right next to it are called the dual basis, right? Of course, just algebra is a very trivial thing. Okay, we're just saying V inverse equal identity. So writing out an auto product form. All right, so just keep that in mind. So you'll see from now on that these rows play a big role. Okay, so now when we're trying to talk about these change of variables that we're doing, like Schur decomposition, Jordan decomposition, right? We're trying to write A as V something V inverse, where hopefully this is a simpler matrix, has more zeros in it than the matrix A. right? And the reason, of course, is that if I look at A power of n, then we get V star power of n V inverse, right? So we can computing the nth power hopefully more easily if there's more zeros in the matrix A. All right. The way to think about this is to write the V on the other side. So at A, get V, and if A is a square matrix, then you can think of A as a map from Rn to Rn, where the coordinate systems that I use are the columns of the identity matrix, E1, E2, like that. And since Rn is the same as Rn on the left-hand side, I tend to use the same basis on both sides, right? And if you write the matrix A, so you know what the linear operator is, takes x to some column B over here. If you write the matrix A, for this basis, you get the numbers inside the matrix A, right? So if you apply A to E1, you get the first column of A, A11, A12, sorry, 21, like that, right? So you apply A to the first column, you'll go somewhere there, take those numbers, put in the first column of A, right? So once you pick the basis, you fix your linear operator, you write in the numbers in the matrix A. Now suppose what happens if you don't like this basis, right? Say for example, we want to change the basis to V1, V2, like that, V3. These columns don't have to be orthogonal to each other, they have to be linearly independent. And since Rn is the same on the other side, you could also pick the same basis on this side too. Right? So then of course when you express this column x has not gone anywhere, it's staying in the same place. We have to rewrite x in the V basis, but we know how to do that, right? We write this V inverse over there, right? And we need to rewrite B in the new basis, right? So we just write V inverse on both sides, right? Because V inverse B is the components of B in the new basis V, right? Same thing, V inverse X are the components of X in the new basis V, right? Those are the numbers that will go in front of V1, V2, Vn. So those are the components of X in the new basis, right? So you see that if I try to change basis for both the left-hand side and the right-hand side to the new basis to be the columns of V, then the matrix numbers will change from A to V inverse AV. Right? And this is exactly the expression we have over here. So this, for example, the star is just V inverse AV, right? It is the what you write down for the same linear operator A if you use a different piece of graph paper on Rn. Okay? Because of that, this transformation is also called a change of basis. Okay? And many of you learn it in your undergraduate class that way. Okay, but I feel that this rigmarole is actually more confusing than meaningful, so I don't say much about it, but at least in most class textbooks, they will say this is called a similarity transformation, and they'll call this to a change of basis. Here, there's only one, the same Rn is on both left and right because matrix A is square. If the matrix A is not square, then you can pick two different bases, right? So then, for example, you can have a V inverse here and a W inverse here. So if the matrix is non-square, for example, the most general change of base will be W inverse AV, like that. Okay, as long as both W and V are invertible. But that is just generic matrix multiplication, right? And we see it so many times. It will be a royal nuisance to keep thinking of it as change of variable, change of basis. So we don't call it out too much. Now, in Kollmeyer's book, he spends a lot of time in this outer product form. And we will write down, and the reason for that is that these outer product forms are more easily generalized to the infinite dimensional case than the product form that we're going to write. We'll talk more about it when we get there. But so our goal now is just to get to the Schur decomposition. Okay, so we want to get to the Schur decomposition. We'll write it A is equal to Q R QH, right? So where R is upper triangular and Q is unitary. All right. So from the discussion that we just had, we know that the way you should interpret the matrix Q is the columns of Q are what count the most. Okay, so that's what matters. Of course, all the rows of QH, but that is the same as the columns of Q. Okay, so in this case, for the Schur decomposition, we just have to keep our eyes peeled on QR, QH. Later on, when we go to the Jordan decomposition, we have to look at both the columns of V and the rows of V inverse at the same time. Okay, so these decompositions are sort of like irrelevant whether you take A or A transpose. Okay, they sort of mean the same thing. So you have to look at them simultaneously. All right, so how are we going to get this? Okay, so the first thing we observe is that to get this decomposition, it's quite difficult actually. So if you write the Q to the left-hand side, it looks like this. Equal to QR. right? And if you open it up like this, it looks like this: Q1, Q2, Qn, and then R11, R12, R22, like that, right? It's a upper triangular matrix with zeros. So remember, by now when you're working in algebra, you should be used to the fact when you're trying to prove something, don't try to derive the answer. Okay, that's like trying to shoot yourself in the foot before you start the proof. Okay, so it's painful to do it that way. Okay, when you're trying to prove something in algebra, always look at the answer. The answer will tell you how your proof should be approached. Okay, so we'll do that. We didn't do that too much in the previous decomposition because they were fairly easy computations. But in the Jordan form and so on, the computations are large to get to the proof. Okay, they just take a long time. So it's hard to derive these without like getting completely lost. We'll frequently look at the answer we're trying to prove and then go back and try to prove it. Okay, so let's look at this one. Can we guess how these numbers should be computed, right? If you look at the first column on both sides, it's fairly easy. It looks like this: Q1, R11. If you look at the second column on both sides, it starts getting complicated. You get Q1, R12 plus Q2, R22, like that. Okay, then it gets bigger and bigger. So our only hope is to look at the first equation, which is the simplest one. Okay, so that's where we're going to concentrate on for the Schur decomposition. What we see is that if you look at the first equation, it looks definitely like an eigenvector equation. In fact, we would readily call Q1 an eigenvector. So Q1 must be an eigenvector of the matrix A, and R1 must be the corresponding eigenvalue, R11. Right, so in particular, we see that we can rearrange this equation as A minus R11I, Q1 is equal to 0. Okay, so what we're going to do is again provide a proof by decomposition, and the goal is to compute one column Q1 and one number R11 that satisfy that equation, and then multiply by the appropriate Hausdorff matrix from two sides and get a smaller matrix to deal with later on. Okay, so that's the proof, just like the SVD, the LU factorization, and so on. And again, unlike the LU factorization where we sort of knew the process to apply, it's just like the SVD, we have to first find how to find one column of U, one column of V, and what equations they satisfy. Okay, for the SVD, it was also very complicated. We had to say, okay, we had to find a column of V and U that satisfies these two equations at the same time. Right, and it took us a while to actually figure it out. We had to say, oh, those numbers are computed by finding the two norm of the matrix A, and it was big to get there. But once we got there, the rest of the proof was easy. Here is also a similar thing. We need to find this column Q1 and the number R11 such that that equation is true. But again, it's a big process to get that. All right, so we see what is happening over here, right? We have to subtract R11 from the diagonal of the matrix A such that the matrix A becomes singular now, or has linearly dependent columns. All right, so we say the clue is to look at A power of n. Okay, so this, remember when you're doing algebra, it is always hard to try some obvious things, right? For example, we often have to say identity is, say, VV inverse, for example, or something like that, right? We have to make these change of variables. We have to say A is equal to A plus X minus X, right? When we use the triangle inequality, we frequently have to do things like that. We replace identity by something trivial or 0 by something trivial, right? So similarly, one of the most common tricks is to look at A power of n when you want to understand the matrix A instead. Okay, very often A power of n would behave far more simply than A itself, right? So we want to look at A power of n in this case. So actually what we do in this case is that we look at a whole sequence of them. Okay, we look at A power 0, which is defined by identity, A squared, like that. And let's say that A is an m by m matrix, right? So we go up to A m squared and then A m squared plus 1, and we keep going like that. Right. So we said in the last class that if you look at the first m squared plus 1 matrices that we produce, all of these matrices lie in R m cross m. And the dimension of R m cross m is, of course, m squared. And there are m squared plus 1 matrices in that set. So they cannot all be linearly independent. So that set must be linearly independent set because there are too many vectors from that vector space. So we know that there exists constants that depend only upon A, beta I, not all 0, such that if we do beta power 0 identity plus beta power 1, a1, beta 2, a squared, like that. Beta power m squared, a power m squared. It'll be exactly the zero matrix. Right? We can find, of course, if I take all the betas to be zero, I mean, that would be trivially true, but the key thing is that there exists at least one beta that is not zero in the sequence somewhere. Okay? So, all right, so that is this step. Okay, once we reach here, the rest of it is just standard mathematics. So we see that this expression, if I didn't tell you A was a matrix, looks like it's related to the polynomial x, but x is just beta 0, beta 1x plus 2x squared, but x is just an ordinary complex number. Nothing to do with related to this, right? But since this is an ordinary polynomial and an ordinary complex number, we know lots of these things about these polynomials. For example, we know that they have zeros. Since this is a polynomial of degree m squared, right? It has got m squared zeros, right? So we know we can write this polynomial as beta m squared. So let's be a little bit careful now. I don't want to screw it up. Okay. So we know at least one number here is not zero. Okay. Let's say from the right on this polynomial, let's say beta m squared is zero. Well, then this term doesn't exist in the polynomial. We just drop it. Right. So we keep going in and in and in. Eventually, we'll run into some number k, such that beta k, x power k. So this number is non-zero. Okay, so eventually you run into 1. Right? You might come back, you might come all the way down till here, till beta 0. Be careful about that. But some number is non-zero. For example, the matrix A is 0, for example, right? Then you'll end up with this guy, say for example, this one being non-zero, right? So this one can never be the only one, sorry, you cannot come up to beta, you cannot have that all of these are 0 and this one is the only one that is non-zero because that's clearly impossible. Okay, so you will stop somewhere ahead. So either at beta 1 or beta 2 somewhere you will stop. So we can say that k must be at least 1. Right, that's clearly true. Right, so then this is a polynomial of degree k. So we know that polynomials of degree k have exactly k zeros. Well, remember k is at least 1. Okay, if k was 0, we'll be in trouble. So we know that we can write this as x minus mu1, x minus mu2, up to x minus mu k. And notice that I put the beta k outside because the highest degree is not 1 anymore. Okay, it's not this number is not 1, so I put this thing outside. If I multiply all of this, I get the highest power is x power k, and if I didn't have this, the constant front would be 1 of x power k, but it's actually beta power k, so you have to write it like this. Okay, so make sure that you can, at least once in your life, you should know how to prove this theorem. Okay, it's called the fundamental theorem of algebra. Probably, I'm hoping that all of you took a complex analysis class, or if not, there's a sort of a mini review of complex analysis in my notes. You should just try to go through that and prove everything. You should get up to Cauchy integral theorem, and then from there you should be able to prove this for the maximum modulus theorem or something. Okay, so there are many ways to prove this, but you should try to prove this at least once in your life. Okay, just to get a feel that it's not that difficult as it seems to prove that every polynomial of degree k has k zeros. All right. Very good. Okay, so this much is true. Now comes the important part. Okay, so we know that if I pick x to be mu1 or mu2 or mu k, then and I stick it in this polynomial, I get a 0, right? That's the key thing. So these are zeros of this polynomial, these mu's. All right, and there's at least one mu, okay? So the k is bigger than 1. Be careful about that. Okay, so now here's the important observation, okay? And this is the part that is really hard to reach without noticing this connection with polynomials. Okay, if I give you an arbitrary polynomial like 2x squared minus 3x plus 1, I can make sense of that even if I put a matrix inside it. If I put the matrix, for example, 5, 6, 7, 8, I can define that to be 2 times a squared minus 3 times a plus identity, right? And it will be a well-defined matrix. Notice I can only do this for square matrices. I need to take powers of a matrix, and I can only take powers for square matrices. But this will always be well-defined, even if I write the polynomial differently. For example, if I wrote 2x squared minus 3x plus 1 as, something like 2 times, I don't know what the roots are, but let's say it's 5 and 13 or something like that. If I could write it like this, then if I stick the polynomial on both sides, I will still get the same answer, no matter how big the polynomial is. Okay, I would get, if I multiplied all this out, I would still get the same answer. Right? And the proof of this is very trivial. The only thing that we use to prove that this side is equal to that side in polynomial algebra is that complex numbers commute with themselves, and complex addition and subtraction follow the rules of arithmetic. Right? The only difference between matrix arithmetic and complex arithmetic is that matrices in general do not commute among themselves when you multiply them. But if the only matrix in town is the matrix A and its powers, then we're back to commuting among themselves, right? So A squared times A cubed is the same as A cubed times A squared, which is equal to A to the power 5. Right? And that's the only property that matters in this when you're working with polynomials. So therefore, whatever you say about polynomials in one variable is also true about polynomials of matrices. Okay, be careful, huh? If you put a 10 by 10 matrix here, the result of P of A is a 10 by 10 matrix. Okay, if you put a 20 by 20 matrix over there, then the result of the polynomial against a 20 by 20 matrix. So when you evaluate a polynomial at a matrix, you get a matrix back of the same size and shape. But of course, that polynomial evaluation is not done entry-wise, right? For example, if I apply this polynomial to the matrix 4, 5, 6, 7, it is not P of 4, P of 5, P of 6, and P of 7. It is not that. Okay, be a little bit careful about this, because in MATLAB, if you say sign of a matrix, it will not actually compute the sign of the matrix as I'm going to define it, but it will compute it component by component. Okay, same thing with Julia too, which is horrible, of course, that they chose a notation that conflicts with what a mathematician would write down. Okay, so I think now Julia is becoming a little bit more sane. So now they're saying at least that you should put a dot if you want to imply that in front, which means component-wise evaluation. And I'm hoping that now they'll eventually sanitize and say sign of A is actually the true sign of this matrix, which should have been this polynomial. Of course, infinite degree, but you get the idea. It's still a polynomial, right? You just should have been that one. All right, okay? So just be careful when you compute. It's sometimes not what you expect it to be. All right, so this always makes sense, right? So this always makes sense over here. All right, so now come back to this expression over here, right? So therefore, it seems that I can, since I defined P of X to be exactly this polynomial, so this is clearly P of A, right? But this P is what I defined over here. So this polynomial and this P of A are the same thing, okay? I'm using this polynomial to write P of A over there. But we also know that this polynomial can be written like this, right? And we just argued, no matter how I write the polynomial, I'm still allowed to stick the A in there, right? Remember, this is ambiguous. These are two matrices, but these two matrices actually commute, right? Because this is just A's and I's, and this is made of A's and I's. I can write them either way. Okay, be careful, right? We can actually commute those two entries. That's why it is perfectly fine to make this argument. You should, of course, prove this for yourself, right? Make sure that you can actually write this the other way. A plus 13i times A minus 5i. Okay, make sure that you can check those two matrices commute no matter how big that A is, as long as it's a square matrix, right? So therefore, if I write P of A, I'm allowed to stick the A wherever I see the X. I get A minus mu1i, A minus mu2i, dot A minus mu ki, like that. Right? So far, so good? Okay. Now, we know that this polynomial, if you put A in it, is actually equal to 0. Right? That we had from up there. P of A is equal to 0. So we can write that 0 down here now. All good? All right. So notice that what I've done is I've started with the sum of matrices, and I've factored it into a product of matrices. So normally when we factorize a matrix, we call it matrix factorization, right? And we do some algorithms to do it. Notice here the algorithm is subsumed in this computation over here, right? We had to use Newton's method or something to find all these roots, the polynomial root solver. So there was an algorithm, but it was sent off on the side to do some computations. After the algorithm finished, it pumped all these numbers out, mu1 through mu k, right? Then I used that to write this factorization down. Okay, so this sum is equal to this factorization. Okay, so it's a very roundabout argument to produce a factorization, right? So it's fairly sophisticated in that way. But that's what we did, okay? All we wrote was sums of numbers as products of numbers. That's all we did, okay? It's like any other factorization. All right, so we did this, but this, of course, is very important. It tells that the matrix 0 has been factored as a product of these numbers. We know beta k is not equal to 0, so, the 0 was not produced by the scalar sitting in front, so we can ignore it. So let's look at this. We're saying that the 0 matrix, right? This was the 0 matrix from on the top, right? That's the 0 that's sitting over there. Is a product of these matrices. Each of this is a square matrix, right? We know that the 0 matrix is not invertible, so it's a singular matrix. So it's not full column rank at all, or full row rank. Therefore, it follows that none of these can be full rank matrices. Why? If all of these are full rank matrices, then all of them will be invertible. But product of invertible matrices remains invertible, right? Because if A and B are invertible, then A, B inverse is B inverse, A inverse. But clearly the product is not invertible, it's a 0 matrix. So at least one of these matrices must be non-invertible. We don't know which one. At least one of them must be non-invertible, right? So therefore we can now claim what we wanted to claim, right? So we've shown there exists some number. So there exists a mu I in the complex plane such that A minus mu I entity is not invertible. Right? Of course, you could have actually found it. Notice that we could have taken all of these matrices, made them into long column vectors, stuck them into a big matrix, right? And found the null space of that to find the column beta 0, beta 1, beta 2, like that, right? That's how we check for linear independence. We find the null space of this long matrix. Once we find the null guy in the null space, you'll just do Elif factorization. You'll get these numbers. Then you take this from this polynomial, and you at least one root. You need to find all the roots because you don't know which one is going to work. You get all the roots. For each of these roots, you form each of these matrices. For each of them, you do an LU factorization and check which one is whose rank is not the full. Right? It's a long calculation, but eventually you'll find one number mu that satisfies this question. Right? Notice that completely we skipped the determinant, which is how we would normally construct a polynomial. Right? But the price you pay is that you do more calculations now to find this complex number mu. All right, but we don't care. We just needed to find this one guy. Okay, we found him. So once you find him, he's not invertible. That means the dimensionality of his null space, right? So square matrix is strictly greater than 0, right? It has at least 1, so it's at least 1, right? It's a square matrix, so if it's not invertible, it has to have a right null space and a left null space of equal dimensionality. Therefore, you can find a vector v such that this is equal to 0 and v is not equal to 0. Right? So we found our eigenvector and an eigenvalue. We showed it exists. Okay? It's a very tedious computation to actually do it, of course, this way, and nobody does it this way. But from a proof point of view, of course, it's nice because you don't have to say what a determinant is. Right? And you see, you don't need to, but you do have to talk about polynomials of matrices to get here. All right. So now that we have this, the rest of the proof is actually quite trivial. So let's relabel these numbers. Okay. So I'm going to drop the I and the mu. Right. And we're going to call this as A minus lambda I v is equal to 0 instead. Okay. So it's typically called lambda and eigenvalues. We'll call it that. So we found a complex number lambda, and therefore a complex vector v such that this is 0. Right. Now the rest of it is just the same as the proof, right? So now we find a household matrix. So remember, v is non-zero, but we can take the length of v to be 1. We can just divide by some scalar to make the length of v 1, all right? So we can, because v is not 0, we can guarantee its length is 1 by just scaling the vector before we pick it. So now we can find a household matrix H1, which maps v to E1, right? Because they both have length 1. You can do this. Okay, remember these are complex household matrices, so you have to be a little bit careful. Okay, it's not what you think it is. So make sure you look in the notes and you see what is the difference between a complex household transformation and a real household transformation. Okay, there's an extra phase factor you must throw in. All right, so now we're almost done. So we look at this equation. We have A v is equal to v times lambda, right? So we know we need to apply similarity transformations. I'm going to apply H1 from the left because I want to make this v2 an E1. I apply H1 here and it's inverse over there. The usual trick, right? So I'm now left with H1 A, H1H, and you can see a similarity transformation sitting over there, a unitary similarity transformation. Then I have H1V is equal to h1 v times lambda, just like before, right? The rest of the proof is almost identical. So this is easy to do. h1v is just e1, right? We picked our Hausdorff transformation to map the eigenvector to 1, 0, 0, 0, right? That's what we normally do. So all we have to do now is look inside this equation. So we look inside it. Let's partition it like this: alpha. Let's call it A, B, H, C, and D, like before. So A is a number, B is a row or column, C is a column, right? And we partition E1 conformally, 1, 0, and on the right-hand side we have 1, 0 times lambda. Right? The proof is the same as block LU, SVD, QR, right? They all go through this. It's just that the first transformation is to find this transformation, the first one. To produce the zeros in the right place is a bit difficult, but this is particularly easy. So if you multiply this equation out and look at both sides, you get AC is equal to lambda 0, right? From which we conclude that we managed to reduce the problem to a smaller problem. So C is 0, so we have lambda BH 0D, right? And this is a smaller matrix, m minus 1 by m minus 1. And you can take the H1 and H1H to this side instead, right? There's H1, A, H1 Hermitian. Right? So the rest of the proof is by induction. So this is a smaller matrix. You just have to do the proof by induction. I won't repeat it. You've done it so many times now. Right? The base of the induction, of course, is a 1 by 1 matrix. It's nice because it's trivial. So for a 1 by 1 matrix, of course, the Schur decomposition is easy to write. A is equal to 1A, 1H. Right? So that's the 1 by 1 case. Right? For a 1 by 1 matrix, the only way it's going to be singular if you subtract the number from itself. So that's the only eigenvalue discard, so we're done. Okay, so this is the Schur decomposition. So the Schur decomposition proves that any square matrix can be written as a unitary matrix Q, an upper triangular matrix R, and QH. Right? And this is the one that MATLAB will call. Okay, the way, of course, MATLAB computes this is nothing like what I showed in the proof. So what I showed in the proof is, of course, extremely expensive to do. Right? So MATLAB does a very complicated process. Okay, so I'll just give you a few words about it. I should say that implementing this algorithm is not easy to do. Okay, so on top of that, there are issues of whether it actually converges or not too. Okay, it's not as nice as the single value decomposition. The single value decomposition is also computed by an algorithm that looks very, very similar to what I'm going to say right now. Okay, so the way that MATLAB computes the eigenvalues is effectively by computing a power of n, okay? But if you try to compute a power of n on a computer, MATLAB is made for doing matrix multiplication, it turns out it's terribly numerically unstable. Okay, even a squared, for example, is a bad idea to compute on a computer. Okay, remember when we solve ax equal to b, so let's look at this equation. So when we solve this equation, what MATLAB actually solves is a plus e x hat is equal to b. And it's guaranteed that E is close to A in the sense that if you look at the size of E with respect to A, it will be smaller than machine precision times some small polynomial in the size of the matrix, right? Which is the best you can expect, given that you're going to do n-cubed operations. That's the best you can get anyway. So MATLAB guarantees that the computed solution is the solution of a nearby system, exact solution of a nearby system. For matrix multiplication, that's not true. If I multiply two matrices A and B to get a matrix C, right, what you obviously get is something else, C hat, but it is not the product of some two nearby matrices in general. Okay, so this is not true. Even if you're willing to perturb on this side, it is not true either. Matrix multiplication cannot be, the errors in matrix multiplication are very, very, very hard to control. In fact, most of the time, when you're actually designing algorithms, you're trying to avoid matrix multiplication. Okay, which is kind of perverse, right? Because that's what MATLAB is made to do. That's the one thing it can actually do pretty fast is matrix multiplication, but that's the one thing that is numerically the wrong thing to do. Right? So therefore, since we can't compute a squared well, we can't compute a cubed well, and it gets worse and worse as you look for higher powers. All right. So that approach is out, okay? So if you try to do that way, it doesn't work too well. Though that's the first algorithm you're taught in an algorithms class, the power method, which is to compute a power of n. So what MATLAB does is actually something very weird. It's called the Francis QR iteration. It'll do something like this. A is QR, then it'll say A2 is RQ, Q1 R1, right? It'll compute QR factorization, which you do in your homework. Then it'll say A3 is, it'll compute the factorization of this, and it keeps doing this QR factorizations. R2, Q2, like that, and then it reverses. Okay, so it computes the QR, it reverses it, and multiplies it together. Then it computes a new QR, then reverses it and multiplies it together. It does this back and forth, back and forth, back and forth. But it does it far more cleverly than this even. Even if you do it this way, it's actually very slow. Okay, it does something else for it. It reduces something called a Hessenberg matrix, and then it does this, and that is still too slow, so it actually works on something called A minus lambda I with a shift. It does it on this matrix instead. Okay, so it's a very complicated process. And on top of that, we know that there are examples where that algorithm doesn't actually converge. However, the example where the algorithm doesn't converge is numerically unstable. So if we perturb that example a little bit, it'll start converging again. So it's called an unstable equilibrium. So in practice, we've never observed the algorithm to actually fail. Okay, in fact, it would be very amazing to actually find a floating point example where the MATLAB's eigenvalue algorithm actually fails. Okay, we have not been able to find one. Not to say it doesn't exist. Theoretically, it does, but those points are unstable. So it's hard to make them work, to not work in floating point arithmetic. Okay, so it is this process that it does, and this is called the shifted Francis QR iteration. Okay, and it's there in Golub and Venlon for people who wanted to do it. To know more about it, it is there. And a variant of this is used to find the singular value decomposition too. Okay, and we'll talk more about it as we go through the rest of the class. Okay, but this is some completely different technique is used. And as we go through the Schur decomposition and talk about other things, I will refer to these algorithms more and more. Okay, but it does take a while to understand the intuition behind these algorithms. All right, we'll get there eventually. At least we'll say something about it. All right, so we have the Schur decomposition. It's the workhouse. It's done by some complicated algorithm. When the Schur decomposition is done, the numbers on the diagonal of R are actually the eigenvalues. Okay, so that's one thing that I need to point out. So we'll just write it out. So we have the Schur decomposition. You can compute it in MATLAB by calling Schur. If you say eig in MATLAB, and do Schur decomposition, return just the diagonal of R. So we want to claim this. So the diagonal entries of R are the eigenvalues of A. So remember what the eigenvalue of A means. We say A is an eigenvalue if lambda is an eigenvalue of A, if the null space of this is non-trivial. Okay, so a complex number is said to be an eigenvalue of a matrix. If you subtract it from the diagonal of that matrix, the columns become linearly dependent. So the matrix is squared. Same thing as saying the rows become linearly dependent too. Right? It's a very, very special number. These numbers, unfortunately, are not unique. There are usually a bunch of them. And what we're saying is that when we do the Schur decomposition, all those numbers will be sitting on the diagonal of this matrix R. The Schur decomposition is not unique. Right? You have seen in the proof there could have been multiple eigenvalues being produced, so the Schur decomposition is not unique. So the question arises, are these eigenvalues unique? So if I do different Schur decomposition, will I get different eigenvalues? Right? That would be a bummer if that happened, right? Then we only have all of them. So we have to look at that, and that turns out to be a very important question, whether we got them all and how to count them. All right, so let's think why they are things. So let's look at it. So suppose I find one Schur decomposition. I got this guy, right? Now I look at A minus lambda I. Right? If I look at A minus lambda I, of course, the temptation is now to stick the Schur decomposition inside it and see what happens. If I stick the Schur decomposition inside it, I get like this. It doesn't help me. But by now, you realize whenever you see identity, you should do something to it. So we write the identity as Q identity QH instead. And then you see that you can pull out this Q and the QH out of there because it plays no role in this theorem. Right? So you can pull it out. So you can factor this as Q R minus lambda I QH. Right? And we're talking about whether this matrix is invertible or not. Right? If it has no null space, it's invertible. If it has a null space, it's not invertible. Right? This is a square matrix, so that's nice. We know both Q and QH are invertible matrices, right? Because they're unitary matrices. In fact, QH is the inverse of Q. So therefore, if this is going to be not invertible, one of these must be non-invertible. You can rule out these two, so therefore it only will be non-invertible if that one is non-invertible. Right? So we can write down, so lambda is an eigenvalue of A, if and only if lambda is an eigenvalue of R, right? Back and forth, because you can take Q to the other side, right? QH A minus lambda I, Q is equal to R minus lambda I. right? So the argument goes both ways. So A and R, so you do any Schur decomposition, get an R. The matrix A you started with and the matrix R you ended up with have to share exactly the same eigenvalues. All right? So we might have lost track of the count of the eigenvalues, but the numerical values are the same between the two sets. Okay, so what all we need to do is to find the eigenvalues of R, but that is easy. Why? R is an upper triangular matrix. So if I look at R minus lambda I, it looks like this. R11 minus lambda something something something, R22 minus lambda something something, R33 minus lambda something something, and so on, right? It looks like that. And this is an upper triangular matrix, and we know exactly when it is singular or non-singular, right? We know an upper triangular matrix is singular if and only if at least there's 1 0 on its diagonal. Okay, so this is the part that I did not emphasize in the previous part of the class, but now you should all go back and prove that if I look at this matrix, for example, 2, 3, 4, 5, 0, 0, 5, one more, 7, 0, 8, 9, 10, 0, 0, 0, 1, right? So there's 1 0 on this diagonal in the second position, right? Its LU factorization has not been completed, right? Because you cannot find, it's clearly, there's no LU factorization on this guy yet, right? But I still claim that this matrix is singular. Okay, it is both rank deficient, is row and column rank deficient. So all of you should go back and in your head do Gaussian elimination and show how this 1 0 can be used to produce an entire row of zeros at the bottom by doing Gaussian elimination. Okay, you should go back and look at it. Or the other way is to show that there's an even easier way to show it is rank deficient. You write down A, B, C, D is equal to 0. And just guess what A, B, C, D should be. Okay, it should be fairly easy to do, so you should try to do it. Okay? Okay, make sure you try to do this calculation. Okay, it's non-trivial. Okay, there's nothing obvious about it, so you should do it at least once in your head to see how you would find A, B, C, D in this case. So make sure you know what's going on. Is it okay? All right, so be careful, because this part is clearly invertible. So if you look at this bottom portion, it's an upper triangular matrix with non-zero diagonal, so it's clearly an invertible matrix, the bottom part. Okay, so that part does not play a role in this game. Okay, so you have to use that fact, and then it should be fairly easy to find A, B, C, D that satisfy that equation. So you know that matrix is non-invertible. Okay, so we know exactly when a diagonal matrix is going to be non-invertible. So lambda is an eigenvalue of R if and only if lambda is equal to R II for some I, right? It has to be one of the diagonal entries. That's the only way you're going to introduce a 0 in R minus lambda I on the diagonal. If you pick lambda to exactly match one of the diagonal entries. Right? So therefore, the diagonal entries of R are exactly the eigenvalues of R itself, and therefore exactly the eigenvalues of the matrix A too. A cannot have some other eigenvalue. Right? Even if you compute some other Schur decomposition, you'll guarantee to reproduce the same numbers on the diagonal. Maybe in a different order, that's for sure. But the same set of numbers will show up again. Okay? That's important. Right, so we know the eigenvalues of matrix A because we know they're just the diagonal entries of matrix R, and that's why the Schur decomposition is useful. Okay, however, remember what we were after originally was computing A power of n, which means we have to compute R power of n, and we know that R power of n is hard to compute because other than the diagonal entry, everything else is hard to do. Right, all of these are. Then there are formulas for these which are not too bad, and the formula for that is even harder and harder and harder and harder. It becomes harder and harder as you go away from the diagonal. Okay, and there are formulas for these, and he actually gives the formulas for this. That's called Newton's recursion. So it can be done, but it's like a nasty set of formulas. Okay, so people usually don't do it, and these formulas are also unstable. Okay, if you actually try to compute them in MATLAB or something like that, they produce nonsense numbers after a while. All right, so what do we do? Right, so the idea then is to ask ourselves, can we produce even more zeros inside the matrix R? Right, so that's what this is called the Jordan's decomposition. So we need to produce even more zeros, but it turns out you cannot produce more zeros with a unitary Q. Okay, the Schur decomposition is useful because we are applying only orthogonal matrices to the matrix A during the algorithm, and therefore it is numerically stable. Multiplication by an orthogonal matrix is numerically stable. Okay, so if I take a Q and apply it to A, and I look at its computed version, you can show it's actually the exact Q applied to a nearby A. you can show that this will be true. Times n, I think. Okay, so multiplication by orthogonal matrices or unitary matrices is completely stable, whereas multiplying two arbitrary matrices is not. Okay, so multiplication by orthogonal or unitary matrices is perfectly fine in practical computations, and that's why, of course, the FFT is so useful. The FFT or the Fourier matrix is a unitary matrix, so taking the FFT is numerically stable. Right, we can do it. Whereas the Laplace transform and the Z transform are not unitary matrices, and in general, applying them will lead us into trouble. Okay, so we don't compute Laplace or Z, right? And so therefore it's okay. But unfortunately, if you want to produce more zeros over here, then it turns out that this cannot be unitary matrices anymore, and we don't compute those decompositions, but they are there. So what we're going to show is that V can be written as V, J, V inverse, where the matrix J is actually bidiagonal now. Okay, and not only the matrix J is bidiagonal, you can actually find simple formulas for J power of n. Okay, it's actually a very special bidiagonal matrix, so we can easily find simple formulas for J power of n, and not only simple formulas for J power, but also simple formulas for any polynomial in J is easy to find. Okay, so therefore it follows that you can also find any. Okay, so let's write it all out. Okay, so we're going to write it out. So when we're doing calculations, so in this class so far, when we did difference equations, we saw that the expression that arose most often was a power of n, right? For example, the transfer function, the impulse response, for example, was just a power of n times step function, right? The right-going impulse response was this. When you're talking about differential equations, you'll see that the matrix that you get is the impulse response will be e power of at times the step function, where by e power of a, you just mean another polynomial, okay? Just like, remember, a power of n is a very trivial polynomial, right? It's the polynomial x power of n. When we say e to the power of a matrix, we just mean some other polynomial at which you're evaluating a. What is the polynomial? The polynomial for e power of x, of course, is 1 plus x squared over 2 factorial. Of course, the polynomial is infinite degree, but still a polynomial, okay? Don't worry about this infinite stuff. This thing behaves so nicely, you might as well think of it as a polynomial. That's the polynomial. So e power of a is just defined to be the way we define for polynomials. It's just this matrix, like that. Okay, and because that original series converges so nicely, you can show that the series for the matrix will also converge very nicely. So remember, if A is a 2 by 2 matrix, all of these are 2 by 2 matrices, and this is a 2 by 2 matrix. If A is a 3 by 3 matrix, everything here is 3 by 3. So therefore, this is also 3 by 3. All right. T is just a scalar. You can put it inside the matrix A before you do the sum. That's what it is, right? So what is key is this. We notice that for a single monomial, right, if I'm looking at a power of n, right, and if I have an expression like this, it'll be the same as v, j, v inverse power of n. That'll be the same as v, j power of n, v inverse, right? We showed this before. So if I take a linear combination of these guys, if I take summation alpha n, a power of n, right, it'll be the same linear combination of these guys. It'll be summation alpha n, v, j power of n, v inverse. And you notice there's a v and v inverse in every term, so it just comes out. So it'll just be v summation alpha n, j power of n, v inverse, right? But this expression in the middle there, of course, is just p of a. So this is p of a, so this is some polynomial of a. So this will just be v polynomial of j, v inverse, okay? That's why it's important. So for any polynomial, that is true. It's actually true for any rational function, okay? But we'll get there slowly. So therefore, it follows that if you want to compute e power of a, you can compute as v, e power j, v inverse, for example, right? And all of these expressions are going to be trivial once we have that bidiagonal matrix J in position. So we can understand not only the solution of difference equations, but solution of differential equations, and then more complicated versions of these can also be done. All right, so that's what we're trying to get at, and that's why this Jordan decomposition is useful, theoretically speaking. Okay, of course, numerically speaking is a different story. Right? In fact, numerically speaking, it's terribly hard to find e power of a because we have no good formulas, right? If I just have this accelerator to compute r power of n, which is numerically unstable, if I try to use this formula, it's obviously unstable too because I have a squared, a cubed, and so on. So on the other hand, e power of a is like bread and butter for controls people. So without e power of a, they can't do anything with it. So there's a paper by Charlie Van Loon, which is called 19 Dubious Ways to Compute the Matrix Exponential. And one of those ways, of course, is there in MATLAB, but I mean, you still have to compute it now and then. So in general, it cannot be done, okay? Be careful about this. I'm just talking to all the controls people over here. I mean, it's nice to talk about these things, but it's like talking about the rank of a matrix, right? I mean, it's like pulling teeth when you have to actually use it in practice. It's not so easy to do. So these are all theoretical things. Later on, in the last part of the class, we'll talk about matrices for which actually all of these can be computed nicely. Okay, but it's not in the general case. All right, so our goal now is to compute the Jordan form, because once you compute the Jordan form, we can understand a whole bunch of other solutions quite easily. So we want to compute the Jordan form now. Okay. All right. So to compute the Jordan form is a long calculation. So we're going to do it in small baby steps. Okay. So the first thing we're going to do is we're going to. So obviously the first thing you should try to do is you should go home and try to compute the Jordan form of a simple matrix that's upper triangle. Let's say for example 2, 3, 0, 4. Try to find its Jordan form. And you'll see that after a few experiments, the Jordan form is difficult to compute when there's more than one eigenvalue that has the same numerical value. Like for example, here there are two eigenvalues, there are 2 and 4. In this particular case, it turns out that very trivially you can write this as V2400 V inverse. Okay, very easy to write this expression out. Okay, so you see that when the eigenvalues are distinct, the Jordan form is actually quite trivial. You can actually make J to be a diagonal matrix, and you can actually write it down directly from the Schur decomposition. Okay, and you should all go away and try to do this. Okay, but I will not hit upon this simple case. Okay, that is the generic case, and you should check how, if in the Schur decomposition, if each diagonal entry is not repeated, so every diagonal of R is unique, then it's very, very trivial with just Gaussian elimination to go from the Schur decomposition to the eigen decomposition. You get V lambda V inverse directly. And I will not talk about it because most of you have seen this in your undergraduate class in some form or the other, okay? But you should, of course, go away and try it by yourself, okay? That's the easy case. You should be able to do it without the help of anybody else, not even Strang. Okay, so just do it and check, make sure that in this case you can do it. Okay, that's the generic case. That's what's normally taught in an undergraduate class. Okay, so we're going to set that aside. So the difficulty comes when you look at an example where the eigenvalue repeats itself. Let's say, for example, we have 0, 4, 5, 0, 0, 2. You'll see that in this case, it is difficult to make anything work. Okay, so after some fiddling around, you realize, okay, what matters is these eigenvalues that are repeating themselves. That's what prevents the simple proof in this case from going through in this case. Okay, so once you realize that, right, and that takes some effort on your part, then you realize that, okay, I got to organize my R so I know where my eigenvalues are. Okay, where are all my 2s, where are all my 3s, where are all my 4s. You want to organize the calculation so you can keep track of these numbers. Okay, so the first thing we will do, therefore, since we know that we have to keep track of equal eigenvalues, we're going to slightly modify the Schur decomposition. Okay, so the first baby step is to modify the Schur decomposition. Okay, so we're going to modify the Schur to say, okay, we can find a Q such that QHAQ is not just an upper triangular matrix, but such that eigenvalues come grouped in equal values. Okay, so first say there's a number called lambda 1, you get a bunch of lambda 1s, okay? And then you get a bunch of lambda 2s, and then you get a bunch of lambda 3s, like that. Like this, and of course there are numbers everywhere else on the upper triangular matrix, but you're going to group them like this. Okay? We're first going to group them so that we can keep, because if I try to group them and I find that all the eigenvalues, all these are 1 by 1 blocks, then I can switch my proof to this case, which I'm not doing. It's so easy to do, okay? So I'll leave that to you. So I have to only worry about the case when there's at least one block that is not 1 by 1. Then the simple proof just breaks down, and I must do something more complicated to try to go for a Jordan form. Okay. So how am I going to do this? How am I going to group all these numbers on the top together, right? So the idea is that, well, okay, I start with some Jordan decomposition, some Schur decomposition, where the numbers come all scrambled. Let's say I get a lambda 1 here, then a lambda 2, then a lambda 3, then I get a lambda 1, then a lambda 2, like that. And I get some scrambling of these numbers, right? I know that the eigenvalues are well defined, right? We've just proved that. The eigenvalues are exactly the eigenvalues of R. So let's say when I finish the Schur decomposition, I get a bunch of numbers, but the equal eigenvalues are all like scrambled all over the place. So now I want to do another unitary transformation. Let's try to move all the lambda 1s up, then all the lambda 2s and lambda 3s and so on. Right? Our first guess would be, let's try to do a permutation, right? Because we just want to reorder these numbers. So maybe I can pick a permutation P and P transpose and hope that I can scramble these numbers to look like that. However, if you try to do it, even on that simple matrix over here, you'll see that there is no permutation that does the job. If you try to permute, if you try to move some entry here to some entry there, the number there will come down over here, right? And you lose your upper triangular structure. Okay, so you cannot do it by just permutations. You have to do something more significant than that. Okay, so to understand this, let's look at a 2 by 2 case. Okay, so we're going to look at a simple 2 by 2 case. So let's say that R looks like this. There's one eigenvalue here, and there's a number up there, there's 0, and another eigenvalue over here. Okay, so let's say that's what I have. And let's say for a second that lambda 1 is not equal to lambda 2. Why? Because if lambda 1 was equal to lambda 2, then I'm done, right? The two eigenvalues are together. It's a 2 by 2 example. There's nothing to talk about. We should just go home. So let's assume that that's not the case. Okay, so we have two different numbers. And now I want to change the Schur decomposition such that the lambda 2 actually goes to the top and lambda 1 comes to the bottom. Okay, so I want to find a Q. I want to say find a orthogonal matrix Q such that QH RQ has the lambda 2 on the top, the lambda 1 at the bottom, and some number up there. Okay, I want to swap the two eigenvalues. Notice that if I try to do a permutation, I cannot do it. If I try to apply an exchange matrix, this alpha will come to the bottom. Okay, so you'll get a lower triangular matrix that's no good for us. Okay, so we need to do something else. So how do I do this? Okay, the idea of the proof is actually quite trivial. Just repeat the proof again. Repeat the proof that we just went through for the Schur decomposition. Remember when we did the proof for the Schur decomposition, we first found a number lambda such that AV equal to lambda V. And then in the first stage of the proof, we produced the number lambda on the top. Like that, remember? The lambda came on the top. Right? So clearly the simplest proof would be just to repeat that proof in this case, but now making my choice of lambda to be lambda 2. Right? So all I need to do is to convince myself that lambda 2 is an eigenvalue, which I already proved, but I need to find an eigenvector for it. Right? So let's try to do it. You really have to produce the eigenvector. You can't assume it exists. Okay, you have to think carefully about the statement. Okay, we never proved that eigenvectors exist for every eigenvalue. We proved there's one eigenvector for every eigenvalue, but that's about all we proved. Okay, so be careful about that one. Okay, so that I want to appeal to. I just do it in this case by raw. So to find the V, I subtract lambda 2 from the diagonal. Then I do AB is equal to 0, 0. Right? I know lambda 1 is not equal to lambda 2, so I can take A as my basic variable, and B is my free variable. Right? So I can take AB to be, I can take A and B like that. Right? I can take B to be 1 and A to be, A minus B to be alpha divided by lambda 1 with a minus sign, and that's 0, 0. Right? So that will be my solution. All right. So clearly if I pick lambda 2 as my eigenvalue, there's a V such that R minus lambda 2I times V is equal to 0. This V is not 0 because there's a 1 sitting over there. Remember, I cannot depend upon the alpha being non-zero. Alpha might be 0, we don't know. All right, so be careful about that, okay? So we have to produce a non-zero that is not dependent upon some of the other numbers we don't know. In this case, it is 1, right? So therefore, I have an expression now that RV is equal to V times lambda 2. And I'm going to repeat the proof from before. I find a Haushofer matrix, and I go H, H, R, H. I know I'm going to get a lambda 2 over here, 0 over here, something there, something there. Right? If I repeated all the proof again, I'm guaranteed to get a 0 in the first column with the Haushofer matrix that maps D to E1. Okay, so far so good. Okay, but remember the proof also has that this should be lambda 2. How can I prove that lambda 2 is over there? Well, there are several ways to do it. One is go back to the theorem we just proved that said that for matrix R, the eigenvalues are the numbers on its diagonal. So we know both lambda 1 and lambda 2 are its eigenvalues. We know a similarity transformation will not change the eigenvalue because this is an invertible matrix. So if I subtract lambda 1 from this diagonal, one of the diagonal entities has to go to 0. Therefore, this must be a lambda 1. Otherwise, there's no hope of lambda 1 being an eigenvalue of this new matrix. Okay, that's one way. The other way, that the proof that I have in the notes, is to look at it like this instead. Okay, so, and this is also a very useful technique to know, so I just know how I'm knowing two things. So remember, we already showed that if you take the trace of a matrix, the trace can only be done for a square matrix, right? So it's the sum of the diagonal entries. Then we show that the trace of AB would be equal to the trace of BA, like that, right? So inside a trace, you can compute the matrices even if the matrices are not square. Okay, you should think very carefully about that statement. You know that the trace can only be taken of a square matrix. So you know that neither A nor B has to be square, but the product has to be square. Right? Then you can convince yourself that B times A will also be another square matrix. All right? And therefore the trace is well defined. So these two matrices can be of different sizes, but this equality is still true. Right? But so the trace of QH RQH then is the same as the trace. So think of this as B, that as A, and move this over to the other side, QH, which of course is just the trace of R. Right? So the sum of the diagonal entries cannot change because of a similarity transformation. Therefore, before the transformation, the trace was lambda 1 plus lambda 2. So after it, it has to be lambda 2 plus lambda 1 again. Okay, so the second number has to be lambda 1 still, because otherwise the trace would have changed. Okay, there's another way to prove it. All right. So we showed that there's a unitary transformation that will exchange the two eigenvalues and put some new number up there. We don't know what that is. We don't care about it. All right. So now we can use this to reorder this mess over here to look nice and pretty like that. How are we going to do it? Well, we just do something like a bubble sort. Okay, so let's draw some pictures. Okay, let's erase this. So we'll do something like a bubble sort to sort these eigenvalues now. So let's look at an example. Let's say that I have a lambda 1 up here, then I have some nonsense, and then I have a lambda 1 up here, and say some lambda 2 up there. Okay, and then some stuff going like that, right? So my first number here is lambda 1, then I don't get any lambda 1s until I come here, right? And I want to move this lambda 1 all the way back up there to the 2, 2 position. So the way I do it is like this. I look at these two rows on the main diagonal and these two columns that intersect the main diagonal. Right, if you look at this little 2 by 2 matrix sitting over here, it is the one that I started with. Okay, so lambda 2, lambda 1, and I want this lambda 1 to come to the top. I want to exchange it like that, right? So I apply a matrix I, H, I like that, and I apply its transpose on this side, I, H, summation I. Right, so this H is 2 by 2, this H is 2 by 2. So when you apply by this matrix, it only messes with these two rows. From the left, it leaves all the other rows untouched. When I multiply by this block diagonal matrix, remember this is a unitary matrix because this is unitary, this is unitary, this is unitary. You can easily check this whole thing is unitary. When I apply this from the right, it only messes with these two columns. It doesn't touch any of the other columns. Right? So you see the only numbers, notice that all these numbers are zeros and all these numbers are zeros over here, like that. So when I apply by this matrix, all of these zeros will be preserved, right? Because H times 0 is 0, so those zeros don't change. When I apply by this, on this portion of the column, all these zeros will be preserved, right? All of these numbers will become new numbers, but we don't care, it's in the upper triangular part. All of these numbers will become new numbers, which we don't care because it's in the upper triangular part still, right? So the only 4 numbers that actually change and that we really care about is these 4 numbers. But they're going to change exactly according to this expression that we have over here. It's going to change like H, R, H summation, like that. Right? And we pick this householder matrix such that after you multiply by these two guys flip like that, and lambda 1 moves to the top. Right? And then you repeat this process again. So you now apply, so now you store that information in your queues, right? Multiply this into your, accumulate this into your queues, and then you apply. Now you look at these 2 rows instead. These 2 rows and these 2 columns. Now there's a lambda 2 over here, or lambda 3. You've got to flip these 2 now by applying this 2 by 2 matrix. Right? So you apply 2 by 2 this way, 2 by 2 that way, and then it'll flip these 2, and you can embed them in a big unitary matrix and accumulate them into your Q and your QH and on the left and on the right. Right, I won't write down all this stuff, okay, but I hope the big picture is clear that what you have to do, and of course you should go away and your exercise will be forced to write this all out yourself. Right, so by this scheme, you can slowly bubble up this lambda 1 until it comes over there and then you stop. Right, then you go back down, if you find another lambda 1 over here, you bubble it up like that. Then once you got all the lambda 1s on the top, you do the same for the lambda 2s, you bubble them up. Then all the lambda 3s, lambda 4s, lambda 5s, like this, you keep doing this. And eventually, you'll get all the lambdas on the top, then the next distinct number, then the next distinct number like that, okay? So when you're done, these will be all the same numbers, these will all be the same, these will all be the same, but no 2 numbers across the blocks will be the same. You've sorted your eigenvalues nice and pretty. into nice chunks like that. Okay, so this is sort of like the singular value decomposition where we know the numbers are real in that case. We want them in decreasing order. Here they're complex numbers, so there's no ordering possible, but you can keep at least equal complex numbers together. We do that because those eigenvalues are the ones that cause the problem with the diagonalization. Is it okay? So this is the first step. Okay, so far this was just still using unitary matrices. So this part is still numerically stable. Oh, it cannot be carried out in practice. In practice, you cannot ask if one floating point number is equal to another floating point number, right? Because, I mean, we make errors, and this is a vacuous question, right? You should never use equality, equal in floating point numbers, right? It's not a meaningful question. So, for example, you might end up with two numbers that look not equal. You do that transformation, and you think you're trying to flip it, but after you flip it, you'll find that the two numbers are equal, for example. Or they're two different numbers entirely than the one that you started with, which is more likely, right? So it's meaningless to ask for this part of the calculation in floating point arithmetic, and MATLAB makes no attempt to order the eigenvalues in any way whatsoever. Okay, whatever comes up in the QR factors, the QR algorithm, it just dumps it out to you, right? Now, unlike the singular values, where MATLAB makes sure it's in decreasing order before it gives it out. All right. So now that we have this part, comes the hard part. Okay, so we are now going to write this in some pretty notation. Okay, notice that when you look at the Schur decomposition in this particular form, so at this stage of the algorithm, we're saying I found a new Q such that my matrix looks like this. Okay, I can block my matrix into square blocks. So this is the main diagonal that goes right through these blocks. On each of these blocks, I have an upper triangular matrix, and I have some stuff up here, like that. All of these blocks are all zeros, right? All this part is zeros too, so there's an upper triangle on each main diagonal block. If you look at any one diagonal block, so this block is called R11, this block is called R22, this block is called R33, like that. If you look at any diagonal block, look at the first one, there will only be one number on its diagonal, lambda1, and then some stuff, and then a 0. Okay, if you look at the second diagonal block, it will look like this. R22 will have just lambda2 on the diagonal stuff, and lambda1 will not be equal to lambda2. Like that. Okay, so that's what we have so far. All right. Okay, this is how far we can go with unitary transformations. So now our goal is to produce more zeros. We want to knock off all of these numbers because they play no role in this calculation. I will just make it look ugly and hard. So we want to introduce zeros in these positions. Okay, that's what we want. The next step is to produce zeros all the way in those blocks. That's what we're going to try and do. Okay, but unfortunately, we cannot produce these zeros by unitary transformations. Okay, so of course, the first thing you should do is go away and look at, for example, take an example like this, 4, 5, 6, 7, 0, 0, 0, 3, 4, 3, and see if you can come up with a unitary transformation that introduces zeros in this block. So here's the blocking that we have, right? And you should see whether it's possible to produce a unitary transformation that will produce zeros in this position over here. Okay, it'll turn out that you cannot do it. So now what we will do, so from now on, or even from the first step, once the Schur decomposition is done, effectively all the nonlinear parts are over now in this calculation. Okay, anything to do with nonlinearity is now basically gone away. So what is left is just a long, tedious Gauss elimination process that is left. Okay, so we'll turn out that we can actually do Gauss elimination on both sides. We can do row operations and column operations, and we can actually introduce a 0. For the price we will pay, so we'll apply an upper triangular matrix on both sides like that. It's just going to be a Gauss transform that will actually produce the zeros in that slot for us. Okay, of course, the price we pay then is this matrix is not unitary anymore. Okay, so we produce a non-unitary transformation, and in general this is to be avoided. Okay, but theoretically we're going to proceed. So we're going to come up with a Gauss transform, produce a 0 over here. So you should all think about it because I already gave this as a homework problem already. Okay, so you should think about it and see which homework problem from before helped you produce a 0 there in that block in this example. All right, and then we will meet next week. Any questions? Okay.